Welcome everyone to the first seminar lecture in our seminar series. So today we've got Ravindra Girivaru from the University of Missouri. He's going to be talking about the generalization of the Franchetta conjecture to bundles on hypersurfaces in projective space.
Thank you very much, and especially thank the organizers for inviting me. It's been a long time since I've traveled, and it's good to be out here. So today I'm going to talk about the Hodge rank of bundles and Franchetta's conjecture to somehow relate So let me begin with the original Franchetta conjecture, which is something that I learned about by watching, by participating in the Zoom algebraic geometry seminars. So the original Franchetta's conjecture says that, well, if you look at the universal moduli space, or the universal family of genus at least two smooth curves, universal family of smooth genus G curves, then any line bundle L on this universal family. So if you look at the restriction to any smooth member of the family, then this is just some power of the canonical bundle. In other words, the only generically defined line bundles are powers of the canonical bundle. So this was stated and proved by Franchetta, but unfortunately there was a gap in the proof. And later on, it followed, they realized that Haller had a proof in the early 80s. It followed from that. And then also a few years later, there was some results of Arbrello and Corralba, which also filled the gap from which this statement followed. Now, very recently, this is probably less than about, I'm sorry, about 20 years. Oh, yes.
So this one,
No, this is just the ordinary moduli spaces. Well, then it's the stack. I'm not very comfortable about these things. I'm just giving you the background. But I certainly know that when they look at hyperscalar varieties that are towards stacks, so maybe here also it's stacks. So then there was a generalization due to O'Grady, and so there's some background for this as well. So here, so you start with smooth K3 surface. Then work of Beauville and Voisin. So they discovered there exists a distinguished zero cycle. It's denoted by O of X. So this is just some multiple of the second channel of the tangent bundle, but the amazing property that it has is that if you look at the intersection product on devices, then the image of this intersection product is a subgroup of the group generated by the zero cycle. So this was a statement, I think maybe early 2000s, that they proved. And then considering that this is such a canonical, so the Chow2, the zero cycle displays a pretty large group for K3 surfaces, but the fact that the intersection product only sees this zero cycle sort of motivated O'Grady to conjecture the following. So the conjecture here is that if you look at again the universal family of K3 surfaces of degree 2g minus 2, then O'Grady conjectured that the image of the Chow2 of the family to Chow2 of any smooth member. So I should have mentioned C is any smooth member, so this is any smooth member, any member. What is the degree of well, so if you all these guys sit in some ambient projective space, and then he conjectured that this image should also sit inside, should be a subgroup of the group generated by this distinguished zero class, zero cycle. And again here, so there were some partial results. The first result was by Pavlich, Shen, and Yin for some values of G, low values of G. And then there's another paper by Beauville, where he proves a weaker version of this for all G. And so that was the story. I mean, it's so much of it is still open out here. And then finally, more recently, maybe I'll just use one of these. Seems quite complicated to use both. And recently there was a generalization, further generalization to hyperkähler. And so this is a slightly different conjecture. It's a cohomological version of the earlier conjecture. And so to set, I'll have to set up some notation, but hopefully this will give you a feel for what give you a flavor of what these conjectures are about. So here they say, well, if you have a smooth projective family or a smooth family of smooth projective varieties over complex numbers, then for any fiber, you can define for any fiber X, you define this group. So GD Chow star X or Chow PX. So GD stands for generically defined cycles, so the same way. So this is defined as the image of Chow P of X with Chow X. And then the conjecture that was stated, so then you have restricted cycle class maps. Yeah. You restrict the cycle class map on X to this subgroup. And the claim is that, well, and then keep coefficients. And then you say, so here's a definition, if you will. So F, so the family F satisfies the Franchetta property for co-dimension p cycles, if this map is so CLP is injected. So this was a this is the statement, this is the definition, but this is in any setup.
I think for the lay people, why this is generalizing the original thing?
Yeah, so there is,
Maybe the second one already, I'm already struggling with.
the K3 surfaces. Well, it's just a way of trying to identify what are the classes which are generically defined. So in this case too, I mean, I haven't said this is a very general formalism, but there is no conjecture in this generality.
How does KC tensor I guess that's canonical class or canonical?
Canonical divisor on the curve, on any
How
curve.
does that relate to your Z delta?
So these are canonical. So the point is to see what are the, so if you see, normally when you have a family, some members might have extra cycles, extra bundles. So here you're trying to identify what are the ones which are generic, which live on the generic member of the family. And when you look at the Lefschetz, I'll soon come to the Lefschetz situation where hopefully that will become clearer.
But I think maybe the point is that in this case, because you only have this basically identified by the degree, that's the only thing that the scene is measuring in that case. It's the cycle pass map. So these two curves, you see its degree, and you use 29 for instance. And presumably in the other case, the K3 set also its degree of your zero cycle is non-zero.
Yeah, of course. Yeah. So in this case, I was about to say in the hypercalar variety, hypercalar situation, I think the original point is that anything which is homologically equivalent to the Boville-Voisin class is also actually rationally equivalent to it. So that's where the generalization comes from. But there are other considerations too. I mean, let me just state the conjecture. This is due to a few latter weird and weird. I mean, in some sense, this is an attempt to understand the generic behavior of in a family. So canonical, every member will have a canonical bundle, right? This Boville-Voisin class is the second Chern class of the tangent bundle. That is sort of there on everything. And you want to understand, well, what are these generically defined classes? Okay, so few lateral weird and real. So they have a couple of papers in which, well, so in the first paper they conjectured that the universal family of hyperscalar varieties satisfies Franchetta for all P. So in this case, this is just a statement about the cycle class map. And they verified for some fourfolds, I think, at least in one of the papers. I'm not sure what they do, but in any case, there are only some very few partial results. And there are more final results due to Bergeron and Shen, maybe. But the point is there are not too many results which sort of in this direction. These are all, I think, relatively sort of new conjectures in the past 20 years or so. So my interest in this is its relation to Lefschetz theory. So, and that's where I'll come back to the, maybe that will make more sense when I, about the K3 surfaces question as well. So relation to Lefschetz theory. So in many of these cases, the families that you're considering sit inside some fixed ambient smooth projective variety. All right, so the question in general is, of course, to give a handle on, you have these you want to prove a statement about these generically defined cycles or generically defined objects, but at least conjecturally, you want to understand, I mean, is there a candidate for this group? In this case, for instance, can you say, like in the Boville was in the K3 surface in the O'Grady's conjecture and the original Franchetta conjecture, you had some generic objects. And in general, if you're given a family and you're looking at generically defined objects, are there any candidates, for which you can prove Franchetta's conjecture? So that's the main motivation. And most of these cases, well, not the curves one, but in general, but the other cases, usually the situation is like this. So usual situation. So you have some smooth projective variety P. And your family is a family of subvarieties inside this. So you have X contained in P cross S. So S is some base, it's a parameter space. So X to S, you have this family. And then most of these results sort of have been proved in contexts like this. But the relation to Lefschetz theory comes from the fact that this is a setting where you can at least identify a candidate for generically defined objects. So let me tell you what those are. So this is so the general principle is the following, or this is something that one can try to see if it holds. So the general principle, and in the case of Chow group, suppose this is a proposition. So let me write down the statement for Chow groups. So usually this is going to be some projective space. So this is, let's say, P. In the situation, so if you have X, so let's call this as Q. You have these two projection maps P and Q. So the general principle, which more or less is established in many of these cases, at least the O'Grady's conjectures, is that the image, so while you're interested in this object, right? So these are your generically defined objects. So in most cases, the statement that you prove, or at least the first thing to check, is whether this is just the image of the classes coming from the ambient space. So this is the thing you're interested in most cases. But in the situation where you are in a fixed projective, smooth projective case, the ambient variety is this guy, and your family is a family of subvarieties in that. So this is the sort of guiding principle in many of these things. And of course, this guy, for instance, in Chow groups, this is true. And if you look at I equals 1, this is what, so in I equals 1, so if you have X contained in P, so let's say this is a threefold, and this is a surface, right? So this statement is what's the infinitesimal Noether-Lefschetz theorem, and this gives you the Noether-Lefschetz theorem, which tells you that under some conditions, if this, so this is typically, so you have some very sufficiently ample divisor inside this, and here you have that pick of P, that is homomorphic to pick of C, pick of X. So this is the general member out here in this family, and in this what's the word for it? So one version, or in the case when you're in this situation, Franchetta's conjecture turns out to be nothing but a Lefschetz type theorem. So this is basically the motivation for me. So I sort of generally am interested in vector bundles and hypersurfaces. So then, of course, so I want to understand if there's some Franchetta for bundles on hypersurfaces of degree D in some projective space. All right, so I want to look for instances of Franchetta for higher rank bundles on this. And the first sort of class of bundles I'm interested in, or I want to look at, is to study sort of Franchetta for ACM bundles. So ACM is arithmetically equivalent. And what's an arithmetically equivalent bundle? So an ACM bundle, so E on X is ACM if it has a maximum possible vanishing cohomology. So if we look at the ith cohomology module of E with twists, then this guy is 0 whenever it's possible for it to be 0. So no equivalent cohomology at all. Of course, it's too much to expect. It's not true when I is 0 or I is dimension X. But this is the maximum possible cohomology vanishing that you can have for a bundle on a hypersurface. And so you sort of look at this. And there are many reasons for studying arithmetically cohomology bundles. The first one is that, of course, these are the simplest of all bundles in some sense because they have no cohomology, and cohomology is one way of understanding bundles. When X is PM, so the degree 1 case, so a theorem of Horrocks tells you that any such bundle is just a sum of line bundles of this form. So this was sort of the simplest class of line bundles, of vector bundles, the ACM bundles on a hypersurface. And the other reasons are, so you had this statement out here, which is the Noether-Lefschetz theorem. So when P is P3, right? So this is, of course, another way to state this is to say that any curve in X is a complete intersection curve. It's X intersection another surface, so it's actually a complete intersection. And this conjecture, so this statement, so Griffiths and Harris in the 80s asked whether this sort of can be generalized to the case when X is a higher dimension, a threefold in P4. So another place where ACM bundles appear, as I was saying, in this context of these kind of theorems is so the Griffiths-Harris conjecture. The Griffiths-Harris conjecture, well, or the question they ask is, if you look at X in P4, right? So there's a hypersurface, deviating 6. So their question was whether any curve, so if you take a curve inside of this, so these are all dimensions out there. So the question was, is C an intersection of X with some surface X in P4? Well, surfaces in P4 can be pretty complicated. So they were asking whether that's the sort of complication you can expect when you're looking at the structure of curves. And maybe 3 years later, this was perhaps in 1982, or maybe in 1985 or so, Voisin sort of proved that the answer to this question is no. So in other words, she gave explicit computation or explicit constructions of curves in any smooth hypersurface, which cannot be obtained as a intersection of the surface. So of course, I'm sort of probably omitting many things. So here X is general, or even very general in the original statement. But Voisin proved that in fact this is not the case.
This is related to the integral Hodge conjecture.
That is now being shown to be related to the integral Hodge conjecture. And then later on, in early 2000s, when we started studying ACM bundles more systematically, so this is a result that I proved with my collaborators, Mohan Kumar and Prabhakar Rao. So what we did was we sort of gave a theoretical framework to Voisin's examples So these were sort of very solid explicit constructions, but using ACM bundles, we showed that there are plenty of such curves. So the conjecture is far, far away from being true. And one of the things that we use is that X has many non-split ACM bundles. So for each rank, you can, in general, you can construct many ACM bundles which are non-split. And every time you have a non-split ACM bundle, you can show that you can construct a codimension 2 or say a curve inside X. And if the curve were of this form, then that implies that the ACM bundle is split. So, but there are plenty of non-split bundles, so there are plenty of curves which are not intersections. So that's the first place where this sort of thing made its appearance. This class of bundles at least made an appearance for me. And so when I sort of heard about this Franchetta conjecture in a recent talk on ZAG, so I was trying to sort of see if one could study these further in this context, in the context of ACM bundles. And so for that, there's a very interesting property that these ACM bundles have. So you have X in, so let me now try in the situation here. So I have a bundle, ACM bundle E on X. Now if I resolve this bundle in the projective space, so that has a very nice resolution. So there is a sum of line bundles. Let's say AI, and there's another sum of line bundles, BJ. It turns out that E has a very beautiful resolution like this, a minimal resolution, but this is on X, and these are on projective space, and this matrix, because this is a torsion kind of projective space, this is like a square matrix, and it's a matrix whose entries are homogeneous polynomials. I already call this F1 to make my notation simple. So I have it. Now, when phi is linear, so when all the entries, the non-zero entries are linear polynomials, in that case, E is called Ulrich. So Ulrich bundles are sort of are of great interest nowadays. There are many papers on Ulrich bundles, and theorem again in the 80s. So I think Ulrich bundles were first systematically studied by Eisenberg. They were introduced by Ulrich and then studied by Eisenberg and Schreier and others. But the theorem. The big theorem in this case, in this context, is a theorem due to Herzog, Ulrich, and Backelin. And they proved that any smooth complete intersection, but let me just write hypersurface, that's what's of interest to me. Hypersurface supports an Ulrich bundle. And this construction comes from algebra. I think they use Clifford algebras and stuff like that. And using that, they show that every smooth hypersurface actually supports an Ulrich bundle. So since every hypersurface contains a bundle of this sort, of course, it might happen that the ranks are not constant. Lots of things might be happening out here, though the resolution is sort of very simple, but the construction is not transparent enough to tell you many things. But in the context of Franchetta's conjecture, so one question that one can ask are whether these are generically defined. By this, what I mean is, if you look at the universal family of hypersurfaces, so XD and SD, and then you have this. So the question is, well, is there a bundle E on XD, which is flat over the base, such that when you restrict, 25 gives you those Ulrich bundles that we constructed. So it's like one of these things where, for instance, when you're studying moduli spaces and curves and so on, so oftentimes people try to prove the existence or non-existence of Poincare bundles. So these are so that's sort of a version out here. So on one hand, of course, it's sort of a very nice question that you can ask as an extension to Franchetta in this context. But on the other hand, really the only tool from what I can gather by reading some of these papers is the Lefschetz principle. In most cases, at least the generalizations to zero cycles and so on, in most cases, there's always an fixed ambient projective space. And most often the Franchetta sort of conjecture is either made or proved or verified by checking the Lefschetz principle, which is to say that the generically defined objects are the ones which are coming from the ambient variety. All right, so there's this question on one end. On the other extreme, like I just said, you can verify. So question prime. So does the Lefschetz principle hold, or the Lefschetz condition? But on the other hand, if you look at the Lefschetz principle, right? So the Lefschetz principle says that generically defined bundles on these on members of this family are restrictions. So generically defined. So now I'm going to ask, is the Lefschetz? So all these questions. So this question can be asked in the context of general ACM bundles, not just Ulrich, but you can ask for any ACM bundle. Does the Lefschetz principle hold? But by the Lefschetz principle, if the Lefschetz principle were valid, then generically defined bundles. So this, by Lefschetz principle, if it holds, tells me that these are just restrictions of ACM to the hypersurface X. But any ACM on projective space is a sum of line bundles. So if the Lefschetz principle were to hold, then this is basically telling me that the only generically defined ACM bundles are the trivial bundles or sums of line bundles. Right, so these are nothing but direct sums OXAI. So these seem to be sort of two opposing ends of one sort of a question. On one hand, the Ulrich bundles are highly non-split; they're in fact simple, I think, in most cases. So they're on the other hand, if the Lefschetz principle were to hold, then this is sort of telling you that the bundle is a sum of line bundles. It's a trivial bundle in this sense. It's a sum of line bundles. It's completely decomposable and so on.
Do ACM bundles with deformations, they're not homology, right? I mean, in principle, I guess they could.
But the deformations of bundles are sort of controlled by the end of E.
Yeah,
so
end of E is you don't know what.
If you knew end E was ACM, for instance, that would imply E is a sum of line bundles. So the end E is end E is one tool that you sort of. In fact, that would be my next theorem. So there are these two questions. So when you want to ask a question like this about bundles in general, well, you can ask for a theorem or a criteria in terms of the rank, right? You can say, well, let's fix a rank and ask ourselves under what conditions can you answer either of these questions, or you use some other sort of invariant. So if I followed the rank. So if let me first talk about the rank criteria and what kind of questions there are, and more importantly, what kind of results. So rather criteria based on rank, so rank of the bundles. So in this case, there is a very, again, there's a conjecture in the 80s, and this is due to book-wide dual and triad. And this basically said that if you take any smooth. So now this is not a generic behavior, but any smooth hypersurface then any non-split ACM bundle has rank R at least 2 to the n minus 1 over 2 and take the floor of that. So a good way to think about this is you look at the spinor, the quadric hypersurfaces in that particular dimension. Every quadric hypersurfaces have these very naturally occurring bundles called the spinor bundles, and their rank is equal to this number out here for every n. And so they basically conjectured that you cannot have smaller rank ACM bundles in that particular dimension than the corresponding spinor bundles. So I tend to think of this as a Lefschetz theorem, as an analog of some sort of growth in Lefschetz theorem. So based on this, and then we sort of made a conjecture. Now, if you sort of drop the dimension, just like in the Lefschetz theorems for Picard groups, now if you assume that D is sufficiently large, and then this is X is general, right? Then the same sort of a statement, any non-split ACM bundle has now rank at least 2 to the n plus 1 over 2. And we had some precise lower bounds for D. So these were sort of, so Lefschetz theorems always come in pairs, and this was a pair of conjectures that one existing and that one we made. And so this is basically telling you that, you know, there are no low rank ACM bundles, and this result, in this case,
Second conjecture is actually general, not very general.
yeah, it's not very general because ACM bundles, they form a bounded family, so there are only finitely many subvarieties. See, normally you have these countable things that you have to throw away, but because this is ACM, you can show that in the presentation, in the resolution that we had F1 to F0 to the twists that arise, they are sort of bounded. So you only have finitely many families like that. And so what you throw out is only a finite union as opposed to a countable union, and therefore it's only general. In the second one, first thing is that there are counterexamples if you don't take sufficiently high degree. And the second thing is that you're trying to sort of generalize, these are sort of been inspired from the Lefschetz theorems. And in Lefschetz, in Noether-Lefschetz, for instance, if you remember, if you take surfaces in B3, then you want your degree to be at least 4. And the corresponding thing for Chow groups is DE greater than or equal to 2n minus 2 or 2n or something, 2n. So this is the sort of inequality where for instance, the block in the Lefschetz conjectures for Chow groups, n is a dimension. So when X is a surface, D is at least 4, and then 6 and 8 and so on. Well, let me just say that the conjectures in that case would be that the conjectures are all integral. So this is Q for all I less than n. This is very general. This is Lori's conjecture. And for the block balancing conjecture, you would have, there's nothing on, was there something on D for the block balancing conjectures? I think there was no condition. There's for any smooth. And then in that case, you have Chow I X Q is isomorphic to Q, but now you have for all I less than dimension X over 2, so N over 2. So it jumps by 2.
It depends, yeah. If you want more connectivity, then you have to require very
Right. I mean, you have to sort of weaken your sort of, you have to make a hypothesis stronger to get a little more in lower dimensions.
This is existence of a bundle.
I know. I'm saying there's more to, yeah. So this is an existing conjecture which had no connection to Lefschetz theory. But when we started sort of looking at ACM bundles in the context of Lefschetz theorems, then analogous to the Lefschetz case, we realized that this could be like a, this is for any smooth without any requirement of this. So this is like the Grothendieck-Lefschetz theorem for ACM bundle or conjecture. And so the belief that they always come in pairs, so motivated us to make this conjecture. And then this conjecture we've sort of verified. So this is verified for the base case for n for r equals 2 and r equals 3. So r equals 2 will tell you, so r is 2. Maybe let me write down the statement since I'll get questions. Yeah, so this is something that I know a bit more about, so I'm happy to answer more questions than the first part. So let me write down the statement, and then you'll see. So, so the BGS conjecture, right? So the theorem that we know out here is if you look at x in x in P5, then R is R is at least. Oh, I think let me let me start from this statement. So okay. So when X is P5 smooth, right? So then the result of Klepper says that any rank 2 ACM bundle is of the form OXA direct sum OXB. Okay. And then Tripathi proves the same result, similar result for a rank 3 bundle. If no, this should be
5 plus 1 is 3, and 2 plus 3 is 8.
So
it has to be at least 8.
So maybe this is
Something's very fun.
right. Okay, let me not write this here. Okay, so yeah. So this is certainly true that when X is P5, right? So N is
Yeah, but it
4.
doesn't fit in the, I mean, you have X being Pn plus 1.
So N is 4.
R is bigger than 2 to the.
Right.
Oh, you're looking at.
N is 4. Let me work it out. So N is 4. 4 minus 1 is 3 over 2. So this is 2. Right? Maybe this was P6. Right, that will work. 4 and 5, yeah. So if this is 5 minus 1, 4, so yeah. So now this is 2 square, which is 4. So the BGS conjecture would say that R has to be at least R has to be at least 4. And this was known due to Klepper for the rank 2 case. And for by Tripathi, this was known for rank 3 ACM bundle splits. So this is for any smooth hypersurface. And now this, which is the generic BGS.
I'm sorry, I have a question.
Yeah.
If I give you, like, how do you know if there is even kind of a large enough? You know, for all large R, even for fixed R, is it easy to see that
There exists bundles.
there exists a lower bound?
Oh, there
Or
exists.
given X?
Yeah, there is a heuristic actually. If you look at the matrix phi,
Is it known?
yeah, this comes from so so the ACM bundles. So there is a resolution F1 to F0 to E, and you have this matrix phi, and you look at the minors of this. So this is rank R. So you got to look at R cross R minors of this guy. And this follows from by studying the variety defined by those R cross R minors, and you know how to compute the codimension of that. It follows from some dimension calculations, yeah. I can even tell you, for instance, no, just the, in this case, just the,
Yeah, but yeah, okay. But you're saying that just explicitly, given this resolution, you can compute a lower bound for any given.
yeah. That's where, well, in this case, at least I know that the motivation comes from spinner. And for the spinners, I think the calculations they did was by computing the minors of those R cross R minors of this, of any general matrix like this. And I think Klepper's proof is essentially that, if I remember. I mean, I haven't read the paper, but it sort of follows from our sort of, this is a commutative algebraic approach. But if you do so, okay, so let me state the result here, and I'll tell you how we prove this. And that way, it's very easy to sort of prove this just by looking at the ND, by looking at the endomorphisms of the bundle E and calculating the deformation space and so on. So the generic BGS case, so if you have X in P4, you look at degree D hypersurfaces in P4, where D is at least 6 and X is general, then this tells you the same result that any rank 2 ACM bundle X. Okay, so this is the result with again Kumar and Rao. And then we have a similar result for any rank 3, but at least most of the cases for rank 3 with 3 conjugate. And once you know it for P4, you can prove the same result for P5 by just restricting it. Because an ACM bundle, if it restricts to a hyperplane and it splits, then it splits to begin with. So in this case, so the main thing that you prove is that H2 of ND, this whole module, so this becomes 0. And so you sort of work out a bunch of vanishings, and those vanishings, as soon as the dimensions sort of grow, those vanishings become more and more easier to prove. There is no deformation, you actually get it on the nose. For any smooth, you can actually get it on the nose that this guy is 0. And for the lower dimensional cases, you have to do some deformation theory and show that for a general guy, sort of this thing vanishes. All right, so not yet, shall we say? So, well, coming back to the so there's a rank-based criteria, and there's also a non-rank-based criteria going back to this question of the Ulrich bundles. So this is Franchetta for Ulrich. Okay, so Franchetta for Ulrich. So remember the statement for this, the statement of for Franchetta's conjecture of Ulrich is that you know that every smooth hypersurface supports an Ulrich bundle, and you want to ask whether there's a universal bundle which sort of restricts to this Ulrich bundle in each of these guys, in each of the smooth hypersurfaces. So here's the theorem. This is sort of, I guess, still work in progress, but this is joined with this was. So what we show is, something slightly more general. So we show that, well, if X, so I'm going to look at the even dimensional hypersurfaces, and you can prove the similar statement for, just like I said there, for the odd dimensional ones as well. So if you look at a general hypersurface of even dimension 2n, and E is an ACM bundle. And now when I say ACM bundle, I'm not saying it's a split, it's decomposable or not. To take any ACM bundle, now if it's regularity, if M of E, so this is the, if Kastelev-Mumford regularity of E and its dual are bounded above by this number ND minus 2n minus 2. Again, this is a number which appears in the Lefschetz theory, right? So in the Lefschetz theorems, for instance, if you just want to compute the Picard number of a generic hypersurface, this will tell you, the degree bounds out there look like P greater than or equal to 2 plus 2 over n, right? So this is the sort of degree bounds that appear in the Lefschetz theory. Anyway, so if the bundle and its dual has low regularity in some sense, so this is the upper bound for that, and then the statement we prove that is any non-zero Hodge class, so that's the Hodge rank, so Hn of x E tensor omega nx. If you look at any non-zero Hodge class, if this guy has any non-zero Hodge class, then any such class gives rise to a trivial line summand, of E, by which I mean that E is isomorphic to E prime direct sum x over x. So anytime you have a non-zero Hodge class, that will sort of split off a trivial line summand. And for Ulrich bundles, the regularity, every Ulrich bundle actually has regularity 0, it's 0 regular, and its dual has regularity d minus 1. That can be very easily verified. So when n is at least 4, n is at least 2, that is, you have a 4-fold in P5 and upwards, then you can show that if there was a universal Ulrich bundle, then that would imply that there would be non-zero Hodge classes, and as a result, it would split off. And in fact, one can actually, so yeah, in fact, in the case of Ulrich bundle, by sort of using, if your Ulrich bundle sort of has a splitting like this, then E prime in turn is again Ulrich. It'll have the same regularity bounds, and by induction, you can show that it keeps on splitting off, and eventually it's just a trivial bundle. So if there's a universal bundle, it would restrict to the trivial bundle in every fiber, but on the other hand, Ulrich bundles are not split, so there is no sort of Poincaré bundle or universal bundle for the Ulrich bundles that are constructed by Herzog, Ulrich, and Mackel. Right. So every smooth hypersurface has an Ulrich bundle, but these sort of don't form a family, because if they formed a family, you could verify all these conditions, and that would imply that the bundle would split. But the bundles are non-split, highly non-split. So there is no universal family. How much time have I got? I can give you a brief sketch, but this is also a good place to stop. 5 more minutes. Okay. So let me sort of, the proof is sort of, again, it uses an older version. It's a older version of the Noether-Lefschetz theorem. So the idea for the splitting, basically what we show is that the idea for splitting comes from, maybe I'll start with this. So you have a non-zero Hodge class, and this is dimension 2n, right? So then shared duality gives me a pairing Hn E tensor omega n plus Hn E dual tensor omega n 2H2n omega 2nx, which is of course just C, right? And say duality tells you that this is a perfect pairing or a non-degenerate pairing. So if I have a side to begin with, then this tells me there exists a side dual such that this pairing is not zero. Now, but on the other hand, I'm assuming that everything exists in a general bundle or on a general hypersurface. This tells me that my class psi, in fact, deforms infinitesimally, right? So this is like the same thing. Class deforms infinitesimally. If it's of type nn to begin with, then it stays of type nn. So that essentially tells you that this is the kernel of the Kodaira-Spencer map. This to Horn. So remember, you have this family X to S, right? So you look at T S comma S to H, I believe it's n plus 1, E tensor omega n minus 1x. So this tells you that your class is out here, but sort of it's living on a general hypersurface. So it deforms infinitesimally in particular. So under this map, the Kodaira-Spencer map, this goes to 0, so it's in the kernel. But so you're looking at some general number out here, which is, let's say, over some point S. But there's a very nice description for this sort of a kernel, which can be, so you look at the first order deformations in this. So OS, so you look at the local ring modulo the maximal ideal, right? So this is call this phi word x epsilon. So this x epsilon sort of is the first order thickening of x in the fiber direction. So then it turns out that this kernel, you have a very nice, if this regularity condition is met, then you can show that using the regularity condition that this is nothing but Hn E tensor omega n x epsilon restricted to x. So E is my universal bundle. And now, once you have this, then the idea to split this off comes from the following. So you have a pairing H0 E cross H0 E dual to H0 OX, right? So there's always a pairing like that. A section of this is a map from O to E. A section of this is a map from E to O. So you compose them, and that's the global section that you get. So the point is, using this information, you want to show that there's a section here and a section there, which pair to something non-zero, and that's what gives you the splitting. But how do you get this? Now, the fact that this is ACM, which means it has no intermediate cohomology, tells you that you have mapped to Hn equal to E dual, and this is H2n omega 2n t restricted to x. Remember, projective space has dimension 2n plus 1, right? And what are these? These are simple, the boundary maps coming from the Euler sequence. The Euler sequence is omega 1 p to some w tensor O minus 1, right? So this is in some n plus 2n plus 2 dimensional vector space to OP. Now, if I take the exterior nth power, right? So this gives me omega np, and I get OP at the end. So this map, so now if I tensor this with E and E dual, I get a map from H0 all the way to Hn. So those are the boundary maps out here, and likewise that. And now remember, I had, of course, from here I have the restriction map to E tensor where my Hodge classes live. Right, so this is this map out here. But my psi and psi dual, I know live in a general hypersurface, so they actually live in this group, And you can show that this map factors through Hn E tensor omega n x epsilon with respect to x, and the same thing for E dual tensor omega n x epsilon with respect to x. And then you have something here as well. So my psi comma psi dual, well here I start with the psi, I get a psi dual because of their duality, but I know both these guys actually live here. Now, from the regularity condition, I know that these maps are isomorphisms. And the fact that the bundle is ACM, you can see that all these intermediate guys are all twists, right? They're just O minus N, O minus, they're all trivial bundles. So it turns out that both these maps are surjections. So if you start with a psi, you get a psi dual, but both of them lift all the way up to S and S dual. And because this diagram commutes, this thing is going to something non-zero out here. So this thing all the way goes to something non-zero out here. So it has to go to something non-zero out here. So S and S dual pair to something non-zero. And well, once you have a pair like that, that induces a splitting of a summand. And so every time you have a class, a non-zero Hodge class like this, this sort of method will induce a splitting. But on the other hand, like I said, so if Ulrich bundles, if there's a universal Ulrich bundle, then this would tell you that that bundle will have to split, and that would give you a contradiction. So that's.
Are there any questions? Should we check the Zoom for questions? Just in case.
Let you know.
Oh, there aren't any.
Well, or I was the only one.
Yeah, there's nothing you can check. I mean, there's no one coming after us, so we can discuss it. Okay, if there's no questions, then we'll thank you very much again. We'll meet again here tomorrow.